Welcome back to another lecture in organic chemistry. We are going to be going over sections 5 and 6 from chapter 12. Sometimes students ask me, will I have a review session for the final exam? And chapter 12 is a review of all of organic chemistry. So pretty much we're here reviewing chapters 9 and 10, substitution elimination addition, and in applications of synthesis. So 12.5 is titled Retrosynthetic Analysis. And it's a bit of detective work. Now, this is thinking backwards. And as an example, there was an outbreak of some disease. Some guy in Texas got some very strange disease. And they asked him, what did you do in the last hour? What did you do before that? What did you do before that? What did you do yesterday? What did you do the day before? And they found out he had been on an airplane flight as a salesperson. He came on contact with person Y. And person Y was a farmer that had delivered fertilizer to a farm. And on that farm, they had an outbreak of anthrax with their cattle. So that's how this random guy in Texas, I think it was Dallas or something, got anthrax. And so it's thinking backwards, okay? And we use retrosynthetic arrows to do that. This is a retrosynthetic arrow. Now, sometimes you want to do a reaction. Molecule A is going to be transformed to molecule E. And what you do is you think backwards. Well, that could come from D, that could come from C, that could come from B, and that could come from A, okay? And then in your so this is, scratch work. This is retrosynthetic analysis. And then your synthetic answer would, of course, be in the forward direction. A reacts with, some reagent A to give B, and that reacts with, a couple things to give C maybe, and that reacts with something else to give D. And we're not focusing on the numbers here. There are some students emailing me about how to number things. I'm not focused on that. If you have a two-step procedure like hydroboration, you do need to have a step 1 and 2 to separate those two steps, okay, in a reaction. You just can't say that's all just step 1, okay? If you want to call this step 1, 2, 3, 4, and 5, that's fine. Or you could just call it step 1, and then step 1 and 2, then step 1, and then step 1. If you have just one step, like you're adding bromine to something, you don't need to label it. Now, if you cram it all together, then definitely you need to have all your numbers. Okay, how many? 1, 2, 3, 4. Yeah, 5 steps there. Okay, so blah, 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 blah. Okay? All right, so let's talk about retrosynthetic analysis. So this is like the pinnacle of organic chemistry. The book takes you through an example, a very detailed example of trying to change this molecule here to this molecule here. And as always, you want to count the carbons. So, we've got this tert-butyl group here. So obviously nothing's going on there. So we want to count these carbons, okay? There's 2 carbons there and 2 carbons there. So we have the same number of carbons. So no funny business there. We are just changing functional groups, okay? So let's look at the functional group. We're going from an alcohol to an alkyne. All right, so that definitely is a change. All right. And then you want to think about, well, how can we do this? Now, the book jumps into, some answers right away, which I don't like to present it this way, but, they said, this is molecule A, this is molecule E, all right? And this is what the answer is going to look like. You're going to have to transform A to something called B, and that to C, and that to D, and then finally to E. And what they said is you want to actually focus on this step. And a lot of students have trouble with this because we are very linear. We always like to think in the forwards direction. And actually, you want to focus here, all right? You want to think about, well, what can be used to make alkynes? There's only one reaction that can be used to make alkynes. Well, there's a couple reactions, but it comes from a dihalide, okay? And the book talks about this in great detail, a whole page dedicated to what you're supposed to think about and how you're supposed to think about it and how you break it down and begin thinking about it. And basically, you come to the conclusion that this molecule here can be used to make an alkyne, okay? And then you want to think about, well, how do we make that, all right? So then you think about here, okay? So you think about, well, how do you stick two bromines on two different atoms? Oh, I know, I remember. You make that from an alkene, okay? Notice how I don't have any reagents here. I'm just thinking backwards, okay? For example, you probably have a flashcard that looks like this on the front and this on the back. And you probably have something like this. Okay. All right, so you have this on the front of the card. Bromine reacts with what to give you that? And then on the back of the card, you might have this. Okay, this type of flashcard will help you memorize reagents, reactions. Okay, and it'll also help you think backwards. It helps with synthesis. You see, let me back up here and just give you, there's three types of questions in organic chemistry. There might be questions like this, what's the product? There might be questions like this, what's the reagent? Okay. And there might be questions like this. What's the starting material? Okay. You want to have a collection of all of these different types of note cards. Okay. And this note card in particular will help you with synthesis. All right. If you're not flipping through flashcards 2 or 3 times a day, I'm not sure how you're supposed to memorize these things and get familiar with this very complicated analysis, okay? So, basically, we're missing 2 things, okay? We're missing 2 things. We are missing the reagent and we're missing the starting material. So we're given just one thing, this molecule right here. How do we, in the world, make that? There's only one way to make that, and you need to recognize that from a bunch of flashcards. Oh, I remember sticking 2 bromines on all of these alkenes in all of my chapter 9 review. So, or is it chapter 10? I don't remember the numbers. So anyways, so you add bromine to that, you'll get that product. And now we need to think about, well, how do we get to that alkene, right? So that's kind of like the process here that you need to go through. All right. And you want to think about what might intermediate, how do I go from an alcohol to an alkene, okay? So there's lots of different things to think about here. And let me just help you think through the process. And the book has a great deal of examples, worked examples, that take you through very lengthily. Okay, so one of these examples, this is 12.4 example in the book. And I don't even want to look at the solution because I want to try to figure it out and think through with my own words and thoughts what's going on here, okay? And hopefully I'll get stuck and you can see how I problem solve that issue, all right? So first I'm going to count the carbons. 1, 2, 3, 4. There's 4 carbons here. 1, 2, 3, 4, 5, 6. 6 carbons here. Okay, now we increase by 2. So I'm thinking, okay, I bet we can add 2 carbons with acetylene. So I'm going to tuck that back in my mind as an idea. All right. There's also functional group changes. I need to make an aldehyde. Okay, aldehydes. Aldehydes come from alkynes. So I'm going to think about the functional groups here. Aldehydes come from alkynes. So do you see this word come from? So I'm going to use the retrosynthetic analysis to try to figure out what this might come from. So if I have my 6 carbons here, maybe these last 2 carbons are an alkyne. Okay. I trust there's a way to make the aldehyde from the alkyne. So there's my 6 carbons. Okay. Now I want to think about where can this come from? Well, the way that I'm coming back to my increase by 2 carbons. The way to increase by 2 carbons is to alkylate. So I'm going to alkylate this with this guy here and acetylene, right? So I'm going to snap these 2 molecules together. Here's 2 carbons, here's 4 carbons. Lg means leaving group, we know that. And so I can kick off that leaving group and stick on those carbons to get that molecule. Okay. And then I need to think about, how this can come from an alkene. So let's go ahead and now put things together. So I have my 4 carbons, 1, 2, 3, 4. Is that 4? 1, 2, 3, yeah. Okay. So I'm going to hydroborate this because look at how this branching occurs. I need this carbon here to be this carbon here. So I don't want to add a functional group here. That's going to be at the branch. I want to add the carbon at the carbon 1 of the alkene, which will be at the terminus there, which will allow me to connect the alkyne at the end of the molecule with a linear alkane chain. So to do that, I need to do an anti-Markovnikov addition. I'm going to do borane. So here's where I would do step 1 and 2 to separate out these 2 steps in the process. And we get this guy here. Okay. Now I'm thinking back to chemistry with SN2 and stuff like that. The OH is not a good leaving group. So what I want to do is convert that to a good leaving group. I'm going to do so with toluene sulfonic acid. Toluene sulfonyl chloride and pyridine. And that will make OTS, which is a good leaving group right on that carbon. Okay. Then I want to treat this with sodium acetylide. Okay. And that will alkylate this carbon with my 2 carbons. I'll dot the 2 carbons of the alkyne yellow, if I may. All right, so now I have 6 carbons. And then now I need to transform this to an aldehyde. And we know how to do that from our flashcards, probably, that are in our back pocket that we're referring to every 20 to 30 minutes as we worry about the exam next week. And what do we get? Well, we get the aldehyde. And so I'll dot my carbons here so you can see which ones are going to, I'll make them bigger. Okay, so we're adding water, right, technically across that carbon-carbon triple bond. So there's the two H's and there's the O in yellow for the H2O that I'm adding. This hydrogen here is the one from the alkyne. It's actually this one. But we draw it for aldehydes. So that's the target molecule there. Okay. So you'll notice how there's a 1 and 2 here for this step, a 1 and 2 for this step. But I don't need to name this step 1. I don't need to name this step 1 because there's only one step in that step. All right. So that's 1, 2, 3, 4 transformations to get to the final molecule. Let's look at another one here. Molecule B. And I like not knowing what the answers are, so I can kind of think out loud and you can kind of see the thinking process that I go through. So we've got 6 carbons here all in a ring. They seem to be not changing. Okay, so let's count the carbons off the ring. I've got 1, 2 carbons, and I've got 1, 2, 3 carbons. Okay, and that's interesting. So it increases by 1. Okay, so I'm guessing maybe not acetylene is used to alkylate. Okay, because that has 2 carbons. But it could be possible that my big, huge molecule that's given to me as a starting material maybe could be converted to an alkyne, and then I can convert that to a molecule that has 1 more carbon, and then, I could transform that. So maybe, I don't know. So let's begin the and then look at the functional groups. There is no functional group change. I mean, the double bond moves a little bit, but yeah, so that doesn't really help me much at all. So I've scribbled so much here. Let me get some more writing space, and let's think about retrosynthetic analysis. So I'll write these kind of small up here on the top right. I'm interested in transforming this alkene to this alkene. Okay. And I want to think backwards. So I'm taking my product. This is the product now. And I'm trying to think about what that could come from. Now, if you recall, my idea was that you could alkylate an alkyne. So, I mean, I don't know if this is right, but let's think about, first of all, that's a wrong arrow. Let's think about what this might come from. This might come from an alkyne. Okay, so I've got the correct number of carbons there. I've got 3 carbons. 1, 2, 3. And then I'm just thinking like, right, so there is a way to snap on alkyl groups onto the terminus of terminal alkynes by alkylation procedures that we saw in chapter 11. So, this could come from this, and like methyl broma. So there's my 1 carbon fragment. Sometimes you write the 2 fragments if they're complicated, but I'm going to write this simple one just so you can see, because you have to think about the carbon count. So that's why I'm indicating where that carbon comes from. And now how in the heck are these two related? Well, they have the same number of carbons, but sheesh, how do I change that into that? Jeepers creepers. Okay, so I'm thinking that I need an alkene somewhere, right? This is an alkyne. Can it come from an alkene? I mean, yeah, I'm kind of stuck here. So you might be stuck as well. So in this case, you might start from the starting material and think about how you would go from that to that. Okay, there might be 2 or 3 steps. Okay. Now let's back off and remember what we talked about in chapter 12, sections 1 through 4. We talked about different ways to transform alkenes to alkynes. So if you treat this with bromine, this will change the molecule to your vicinal dibromide. And then if you treat this with 2 equivalents of sodium amide, you'll get your alkyne. Okay. And then we saw ways to change alkynes into alkenes by, different ways, like hydrogen Lindlar or something like that, okay, to give you alkenes, okay? So we know how to change an alkene to an alkyne, and we know how to change an alkyne to an alkene. So using that information, we could guess that this could come from an alkene, but I cannot do magic here. The alkyne has 2 carbons there. That would have to be where those 2 carbons are, right there. Okay? And now this becomes a simpler problem. How do I get this double bond to become there? Okay, because that's where that double bond is. Okay? So now I'm thinking, oh, I remember this. This is just, let me show you in the book where we did this problem in the lecture, in introducing things. It's called a functional group. What's it called? I'm lost. Bear with me here. I just want to make sure. Okay, here's yes. So I just wanted to show you. Let's. This is where it's good to take a look at the book. From time to time, you might find something that is useful. So in chapter 9, we developed a 2-step technique for moving the position of a double bond. For example, so here's a double bond in the ring, and then here's a double bond outside of the ring. Okay, so we want to use this technology. It's from chapter 9, and this is reviewed in chapter 12 on the synthesis chapter. Okay, so that's what we want to do. So this is going to come from alkyl halide, and then ultimately that can come from the starting material or whatever. Okay, so all right, so we're there. Okay, it's all scattered in here, but let's begin the synthesis. Okay. Switch to maybe yellow. All right. So I'll go back to the problem and write what we're trying to do up at the top again. Okay. So we're trying to transform this molecule into this molecule. And I'm sure you have a lot of stuff on your scratch paper right now as you're thinking about this. So this is the starting point, okay? So we want to start here, and in the forward direction, okay, the idea was to stick something here, okay? So we want to do hydroboration again. Okay, and this might be different from the book. which is fine. I mean, there's different ways to solve these guys here. And so now we have an alcohol right there. Okay. I want to treat this with a toluene sulfonyl chloride and pyridine, and that makes it a good leaving group. Okay. I want to treat this with a strong base that's bulky, and that will give me the Hoffman product. Okay. Capital H. Okay, so look up the E2 if you forget that. And then here's where we want to do the synthesis of an alkyne. And we want to add 2 equivalents of sodium amide. Okay, so there's my alkyne. Oh my gosh, this is the longest synthesis in the world. If we add sodium amide, and then my bromomethane, I will get, and don't worry, you'll never get something like this on the exam, but this is a learning experience to see how I'm thinking about this. Okay, so now what we have is 3 carbons, and we have 3 carbons. Now, these 2 carbons in the desired product are part of a transalkene, and these 2 carbons are part of an alkyne. So to get to a transalkene, we do sodium in liquid ammonia, and that gives us the target molecule. I'll draw it out. Okay, so there might be better ways. Later on in the class, we'll learn faster, shorter chemical reactions to do this. But for now, this is the best we can do, knowing the technology that we have. So there's, 1, 2, 3, 4, 5, 6, 7 synthetic reactions. Maybe the book has done it in a shorter way. All right. And again, focus on things that are between 3 to 5 steps, okay? And I have, let me just show you here quickly in the book. These are the relevant ones that you should be able to do. Okay. And they're highlighted here, okay? Now these questions, I snipped the problem there, didn't I? I can't go back. It says propose an efficient synthesis for the following transformations, okay? And I want to do problem A, F, and G. And this is number 1213, okay? So let's do 1213A. We want to go from acetylene to, okay, and this is the level of detail and difficulty that we should be familiar with, okay? So what you definitely want to do is think backwards. This is a bromohydrin, okay? That can come from an alkene, okay? Alkenes can come from alkynes, and those can come from acetylene. So let's stitch together our proposed synthesis. We start with acetylene. I'll draw the H's in there. And we treat this with sodium amide, followed by bromoethane. Bromoethane has 2 carbons, and those are going to be the 2 carbons we need to stitch on the end. I kind of glossed over counting the carbons because I could just count really quickly. I'm sorry, I did that part in my head too quickly. So now what we have is the molecule here, okay? And we want to transform that to an alkene, and we can do that with hydrogen and Lindlar, for example, which we discussed earlier in this lecture. And then I can use bromine and water to give me the target molecule. Okay, this is the target molecule. TM. TM is target molecule. So that's 1, 2, 3 steps. This right here is the type of problem you should be able to do. Okay, 1, 2, 3 steps. I know step 1 is technically 2, but we're talking about 3 synthetic transformations. All right, so this is an excellent problem to be familiar with. 1213F. All right, funny stuff going on with the functional groups. We got geminal dibromide. We got a carboxylic acid. So, and count the carbons. 1, 2, 3, 4, 1, 2, 3. So we're losing 1. That tells me right away that it's going to be an ozonolysis. So let's think backwards. What ozonolysis procedure would create a carboxylic acid? One in which is an alkyne with an extra carbon, okay? That extra carbon gets snipped away, and I guess you're forming CO2 in this, but of course carbon dioxide is in the air we breathe, so it just floats away from the reaction. It's not really isolated. Where can alkynes come from? Alkynes can come from alkenes, and I know it must be an alkene because there's... Oh wait, I'm wrong. Good. So my flashcards were messed up there in my mind, okay? So this can come directly from this molecule. Okay? So let's propose our synthesis. This is a 2-step procedure now. So here's our proposal. We want to take this guy here and treat this with 2 equivalents of sodium amide. And that'll get me straight to the triple bond. Okay? I got a little confused. I was thinking an alkene would be used to make that, but we don't need to make that. We have it. This is our starting point. I got mixed up in my mind. So we got this alkyne that we had discussed, and now we just do the ozonolysis. Bubble in ozone, add water, and we get the target molecule. Okay, so this is a 2-step reaction sequence, and that's very good for the level of difficulty you should be prepared for. For problem 1213G, we have a triple bond being transformed to this one, and then it says plus En. That means enantiomer, okay? Oftentimes we don't worry about stereochemistry, but let's just synthesize this, okay? So how do I go from acetylene to that, all right? So obviously we want to count the carbons. There's 2 carbons here, and there's 6 here, okay? So there's 2, 2, and 2. So we know we can react acetylene with 2 more carbons on the left, 2 more carbons on the right to get the total 6 carbons, okay? So we'll do that alkylation. And thinking backwards, we want to think about what this can come from. This can come from an alkene, right? Because this is a bromohydrin again. Bromohydrins come from alkenes, and they give you that trans geometry there, right? And this can come from an acetylene molecule with your 2 carbons on the left and 2 carbons on the right, and that comes from acetylene. So our proposed synthesis would be to take acetylene, treat it with NaNH2, followed by bromoethane, This is just like the homework that we just did a couple days ago. Rinse and repeat. You see, acetylene is bifunctional. It's got that terminal acetylenic hydrogen still, so we could do this again. And yeah, so we get that 3-hexyne molecule. And now how do we get a transalkene? Transalkenes come from alkynes and sodium in liquid ammonia. And that then can be transformed to the target molecule with bromine in water. So that's 1, 2, 3, 4 steps. Okay, so this is a good problem to think about as well. Okay, so 3 to 4 steps, possibly 5 is what we are looking for here in terms of the difficulty. Okay. Let's turn the page here. 12.6, practical steps for improving proficiency. I like their word of the toolbox of reactions. And if you want to fix your bicycle, sometimes a screwdriver is needed, not a wrench. A wrench might be able to do something that a screwdriver can do, but it's more efficient to use a screwdriver, for example. So that's what we're talking about here. You have many different reactions to choose from, okay? And the book talks about creating your own synthesis problems, okay? And I'm just going to read this because a lot of students don't read their book at this point in the class. They're overwhelmed with other classes and things. But it says right here, a helpful method for practicing synthesis strategies is to construct your own problems. The process of designing problems often uncovers patterns and new ways of thinking about the reactions. Begin by choosing a starting compound. Okay. To illustrate this, let's begin by choosing a simple starting compound such as acetylene. All right. Then choose a reaction expected for a triple bond, perhaps an alkylation. Okay. So let's add, 3 carbons. Okay. Next, choose another reaction, perhaps an ozonolysis. Okay. One, two, three, four, 5. 1, 2, 3, 4. Okay. Finally, simply create everything except the starting compound. So you then make the problem. How do you go from acetylene to your carboxylic acid? Okay. And this right here, you've created your own problem. Okay. And you know you can do this in 2 steps. Okay, you can do this now in 2 steps. You have the answer because you've created this, but your friend that you're giving this to doesn't know the answer. They have to figure out how to do that. Okay? Do you see that? So you could put together 10, 20 of these, okay? And you'll forget, right? We don't have photographic memory. And then the next day, you could take a sheet of paper and try to do all of those synthesis and then check your answers, right? The book talks about multiple correct answers, and it's okay to have multiple correct answers. And I like, personally, problems that have more than one correct answer because there's more than one way to solve it, okay? So I'm kind of debating how to do this because it's more work for me and everybody else, but I think it would be a very useful procedure for people to create 5 problems. So for the homework, For 12.1 to 12.4, that last lecture, you're going to create 5 two-step problems that start with, some random alkene. These are just examples of alkenes that you could start with. Yeah. Or start with a random alkyne. All right. Do 2 steps. So take your starting molecule. Okay. Do step 1. Get something else. Do step 2. Get your target molecule. Okay. That would be problem 1. So problem 1, how would you make the target molecule starting from your starting molecule? So you write this out or draw it on the computer. Okay. And you write target, you draw that structure. This is going to be some kind of crazy looking molecule, right? It's just do 2 steps. Don't kill your partners. So you want to write out how would you make that starting molecule, target molecule. Okay. And then you're looking for 2 reactions. Okay. Just 2 reactions. Keep it simple. And you want to do 5 of these. Okay. Okay. Don't put any names on these, and we'll shuffle them up and redistribute them to the class for homework number 2. Okay, so that's homework. That's homework number 1. Okay, so let's do an example. Let's say I randomly pick this alkyne as my starting material, and I want to treat this with sodium in liquid ammonia to give me a trans. Well, there's no stereochemistry there because it's terminal. And then I'm going to treat this with ozone followed by zinc and acid. Okay. And so my problem number 1 would be, how would you synthesize? And I want to write out this. Okay, put a little question mark there. And draw the molecule. Okay, so that's what, hide this. This is the key. Hide that. Okay, this is what you want to turn in. Okay, that's number 1. Turn into number 2, number 3, number 4, number 5. Okay, and try to write nicely and neatly, and we'll shuffle these up, and then we'll give these problems to people for problem 2. Okay, and if you give me something that I cannot do, I will ask you what's going on or something, and maybe you made a mistake. So that's how I'm going to grade this. Okay, if I can't do it, then I know students shouldn't be able to do it. All right, so I'll check all of these to make sure that they're synthesizable, and then we'll hand these out and everything, and we'll let students work on these. So the exam's next week, so try to get this in by, a few days, and we'll see if we can get these redistributed by Tuesday. So try to get this in by Tuesday, and then I'll look over them really quick, and then I'll reissue the homework to be turned in by Thursday. I guess the exam's Thursday, but it'll be helpful activities for us to learn about this. Okay. Now next week we're going to be doing chapter 11, and chapter 11 will not be on the exam, it'll just be homework, okay? So everything we've talked about, chapter 8, 9, 10, 11, and this synthesis, chapter 12, are going to be on exam 4. There is no comprehensive final exam, but as you can tell, chapter 12 is pretty much comprehensive, so it's really hard. And I hope that this homework will help people, be able to solve things and get better with learning the reactions, okay? So let me know if you have any questions, and I look forward to doing your homework because you're going to give me problems, and once I can complete them, I'll hand those out to the class to do, okay? Now, you're going to turn in 5 problems for homework 1, and for homework 2, I'm going to say do 3 out of the 5 problems, and that's kind of how the exam works, right? You have to do 3 out of the 5, okay? Because sometimes you just see it, sometimes you're familiar with this, or sometimes, oh, I'm just so stuck, I'm confused. There might be more than one way to synthesize this molecule, and it's okay to do that in more than 2 steps, but please just turn in a 2-step synthesis, all right? This right here is considered 1 step, all right? This right here is considered 1 step, so this is what I call a 2-step reaction, so be aware of that. Don't get confused by the 1, the 2, all right? We're talking about 2 synthetic transformations, all right? So let me know if you have any troubles, and thanks for watching. Bye.